Welcome back, everyone. We're diving deep into the world of large language models today, and specifically how to train these massive models when we only have so much GPU memory to work with,
That's right. It's a challenge everyone who works with LLMs has to grapple with.
especially when we're looking for optimal performance with those large batch sizes.
Exactly. It's a constant balancing act. You want the biggest batch size possible, but you're always limited by that finite memory capacity of the GPUs.
Right. So could you remind us why batch size is so important when we're training LLMs?
Well, think of it like this. A larger batch size means the model's learning from a much wider range of examples all at the same time. Kind of like processing a whole stack of textbooks at once instead of just one chapter at a time.
Makes sense. So the model is adjusting its parameters more effectively and ultimately learning faster, right?
Yeah, and it lead to more stable training overall.
So it's about finding that sweet spot, big enough for efficiency, but not so big that we run out of memory.
Yeah, and in the LLM world, that sweet spot is usually somewhere between 4 and 60 million tokens per batch.
Okay, so that's the target. But then there's the memory limits of the GPUs. What are the things we need to watch out for during training? What are the main culprits eating up all that GPU memory?
Well, there are four main things to keep in mind: the model weights, the activations, the gradients, and the optimizer states.
Okay, four memory monsters to wrangle. Let's start with the first one, model weights. How can we actually calculate how much memory they're going to use?
For transformer-based LLMs, it depends on a few factors: the hidden dimension, the vocabulary size, and the number of layers.
So the hidden dimension is sort of like the model's processing power, right? Like the number of neurons in a brain.
That's a good way to think about it. And then you have the vocabulary size, which is basically the total number of unique words the model knows.
And then the number of layers add more complexity and depth to the model's understanding.
Exactly. And once you know the number of parameters, the memory required for the weights and the gradients is simply that number multiplied by the number of bytes per parameter.
Right, and that's where the data types come in, like FP32 or BF16.
Right, because the size of each parameter depends on the precision level.
So BF16, which uses fewer bits, would mean less memory usage, right?
You'd think so, but it's not always so straightforward. BF16 only uses 2 bytes per parameter compared to 4 for FP32, but it often needs an additional copy of the weights and gradients in FP32 for stability.
So then why even use BF16 if it doesn't always save memory?
It's a speed thing. BF16 allows for faster computation, so even if it doesn't always reduce memory usage, it can still significantly speed up the training process.
Got it. So let's say we factored in all that, the data type, the number of parameters. What kind of memory figures are we actually looking at for, let's say, a really massive LLM?
Well, a smaller model, something with about a billion parameters, might need something like 16 gigabytes of memory in FP32. But when you start scaling up, the numbers get pretty crazy. A 7 billion parameter model needs about 112 gigabytes, which is already pushing the limits of most GPUs.
Oh, yeah.
And if we get to something like a 70 billion parameter model, then we're talking about over a terabyte of memory, 1120 gigabytes to be exact, just for the weights and gradients.
And then we still have to factor in the optimizer states, which also require a good chunk of memory.
Exactly. That's why memory management is so crucial. We need those clever techniques to make it all work.
Okay, so we've covered weights, gradients, and optimizer states. But we have one more memory monster to deal with, activations. What makes them so tricky compared to the others?
Well, activations are kind of like the model's working memory as it processes information. The tricky thing is that the memory required for activations depends not only on the model's size, but also on the length of the input sequences.
So the longer the text you give the model, the more activations it generates and the more memory you need.
That's right. And batch size also plays a key role here because we're processing multiple sequences in parallel.
Right, so if you're processing a batch of 10 really long documents at the same time, you're going to need a lot more memory for activations than if you were just processing one document at a time.
Exactly.
So how do we estimate that? How do we figure out how much memory those activations are going to take up?
Well, there's a formula that takes into account the number of layers, the sequence length, the batch size, the hidden dimension, and the number of attention heads.
I'm guessing that formula is pretty complicated.
Yeah, it can be, but the point is, it lets us predict how much memory we'll need based on the specific input data and model architecture.
Sounds crucial. So just to give us a sense of how activations can impact memory usage, how much do they affect the overall memory picture?
If you think about it, as the sequences get longer, the memory usage for activations really starts to skyrocket, especially when you're working with large batch sizes.
That makes sense. So as we push for those large batch sizes, activations can become a major bottleneck.
Absolutely, and that's why we need techniques like activation recomputation.
We'll save that for the next section.
So we've seen how those activations can become a major memory bottleneck, especially as we increase the sequence length and batch size. But thankfully, there are techniques we can use to manage this.
Right. And one of the most powerful techniques is activation recomputation. Is that right?
Exactly. Activation recomputation is a game changer when it comes to training large models.
I have to admit, the name makes it sound a bit intimidating. Can you break it down for us? How does it actually work?
Sure. Imagine you're reading a really dense technical paper. You probably don't want to keep every single detail in your short-term memory, right?
Definitely not. My brain would be fried.
Exactly. So you might jot down some key equations or concepts on a notepad so you can refer back to them later.
Ah, so it's like selectively offloading some of that information to free up mental space.
Yeah, it's like creating checkpoints that you can revisit if you need to, and that's essentially what activation recomputation does. Instead of storing all the activations from the forward pass, we strategically discard some of them to save memory.
And then if you need them later during the backward pass, you just recompute them on demand.
Exactly. So we're trading off some extra computation for a big reduction in memory usage.
That makes a lot of sense. But how do you actually decide which activations to keep and which ones to discard?
So there are two main approaches, full recomputation and selective recomputation. With full recomputation, we essentially checkpoint the activations at the transition point between every layer of the model.
Okay, so you're basically taking a snapshot of the model state after each layer.
Right, so if you need to recompute an activation, you just start from the nearest checkpoint and redo the calculations for that specific layer.
So full recomputation gives you the most memory savings, but it sounds like it could also lead to a lot more computation.
That's right, it comes with a higher computational cost, but sometimes it's the best option, especially if memory is really tight.
Got it. So is there a way to be a bit more strategic about it? That's where selective recomputation comes in, right?
Exactly. With selective recomputation, we only checkpoint the activations for the most expensive operations in terms of both memory and computation.
So you're focusing your efforts where they matter the most.
Yeah. And it turns out that for many models, a lot of the memory consumption comes from a specific part of the model, the attention mechanism.
So it's often a prime candidate for recomputation.
Right. And the good news is that selective recomputation can be really effective. Some studies have shown that you can reduce activation memory by up to 70% with only a small increase in computational costs, like 2 or 3%.
Wow, those are some pretty impressive numbers. Are there any real-world examples of where this is used?
Actually, a lot of modern transformer models already use some form of selective recomputation. For instance, flash attention, which is a popular optimization technique, actually incorporates recomputation as part of its design.
So recomputation has become kind of a standard technique for training these really large models.
It really has.
But I guess it's not a perfect solution. There must be some trade-offs to consider, right?
Of course, there's always a trade-off. While recomputation can save memory, it does add some extra computation because you're repeating parts of the forward pass. So training might take a bit longer, but often that's a small price to pay for the memory savings.
Right. So it's another balancing act.
Exactly.
Okay, so we've talked about how activation recomputation can help us manage memory, especially when we're dealing with those really long sequences. But what about batch size? We know that bigger batches can lead to better performance, but they also increase the risk of running out of memory. So how do we find that balance?
That's where gradient accumulation comes in. It's a really powerful technique that lets us effectively increase the batch size without actually increasing the memory footprint of each training step.
Gradient accumulation sounds intriguing. Can you break that down for us? How does it actually work?
Sure, imagine you have this huge data set that you want to use for training, but your GPU just can't handle the entire batch all at once.
Yeah, that's a common problem.
So instead of trying to force feed the model all that data, we can split the batch into smaller chunks called micro batches.
Microbatches. Okay, so it's like breaking down that giant feast into smaller, more manageable bites.
Exactly. And we process each microbatch separately, calculating the gradients for each one. But here's the key difference. Instead of immediately updating the model's parameters after each microbatch, we accumulate those gradients over multiple steps.
So you're basically taking multiple smaller steps towards the final goal instead of trying to make one giant leap.
Exactly. And once we've accumulated enough gradients from a sufficient number of microbatches, we then average them out and perform a single parameter update. This way, we're essentially mimicking the effect of a larger batch size without actually needing all that extra memory.
It's like tricking the model into thinking it's working with a larger batch size, even though behind the scenes we're handling the data in smaller chunks. Pretty clever.
It is, but like any technique, it has its trade-offs.
Right, I was just going to ask about that. What are the downsides?
The main drawback is that it adds some computational overhead. Since we're doing multiple forward and backward passes for each parameter update, the training process takes a bit longer.
So it's a trade-off between memory efficiency and training speed.
Exactly. We need to weigh those factors carefully and find the right balance for our specific needs.
Makes sense. So gradient accumulation gives us another tool for managing memory during LLM training. Anything else we should keep in mind when trying to optimize the training process? Any final tips for our listeners who are eager to train their own LLMs?
One last thing that I think is really important is profiling. PyTorch has a built-in profiler that gives you a deep dive into how your training is running on the GPU.
Profiling. Okay, so we're talking about really analyzing how the training process is working, looking for bottlenecks and things like that.
Exactly. It can tell you how much time is being spent on each operation, how efficiently you're using the GPU's memory, and even where data transfer might be slowing things down.
That sounds incredibly valuable. You could really fine-tune your training process with that kind of information.
It's a must-have for any serious LLM training setup.
Awesome. So there you have it. We've covered a lot of ground today, exploring the challenges of training large language models with limited GPU memory and some of the key techniques for overcoming those challenges.
We talked about the importance of batch size and how to calculate the memory requirements for different model components like weights, activations, gradients, and optimizer states.
We also dug into activation recomputation and how it can significantly reduce memory usage by strategically discarding and recomputing activation.
And we explored gradient accumulation as a way to effectively increase batch size without overloading the GPU memory.
We even touched on the importance of profiling to really understand and optimize your training process.
So hopefully you're walking away with a much better understanding of how to tackle those memory challenges and get the most out of your LLM training.
Thanks for joining us on this deep dive, 6TI. All right, welcome back for another deep dive. Today we're picking up where we left off last time. With these massive language models and how we actually train them. Last time we were talking about batch size.
Yes.
And how important it is to get that just right.
Yeah, finding that sweet spot.
Not too big, not too small.
Exactly. Somewhere in that 4 to 60 million token range,
But then, the real elephant in the room, I guess you could say the elephant in the GPU, is memory.
It really is.
All those model weights, the activations, gradients, the optimizer states.
And it all adds up so quickly.
Yeah, so we talked about a few tricks to try to save some memory.
Yeah.
Like using mixed precision.
Uh-huh.
With BF16 and activation recomputation. Remember?
Oh, yeah.
Like that analogy with the chefs prepping ingredients while things are cooking.
Efficiency is key.
But what if you have this model and it's so huge, it's just gigantic. It just won't fit on a single GPU.
Right.
Even with all those memory-saving hacks.
Yeah.
That's when things get really interesting.
That's when we have to get creative.
That's where we get to data parallelism.
Exactly. Data parallelism, or DP, it's basically just taking your model and replicating it on multiple GPUs. And each one gets to work on a piece of the data.
So kind of like divide and conquer.
Yeah, exactly. Like a team working on a giant puzzle. Everybody has their section.
Okay, so how does that actually work, though?
So in basic data parallelism, you take your data and split it into what we call micro batches. One for each GPU. Each GPU processes its little micro batch. It calculates the gradients, but then we have to keep all those models in sync.
Right, because they're all working on their little pieces.
Exactly, and that's where all reduce comes in.
Reduce.
It's basically a communication operation. It's distributed, and it averages all the gradients and all the GPUs.
So it's like making sure all those puzzle pieces from all the different team members actually fit together.
Precisely. It keeps all those replicas of the model consistent.
Okay.
But here's the thing. The naive way to do DP, it can be a bit inefficient.
Okay.
Imagine each GPU just sits there and waits for all the others to finish their backward pass before it starts to synchronize the gradients.
Doesn't sound very productive.
Not at all. It's like a relay race, and all the runners are just standing around after they hand off the baton.
So much wasted GPU time.
Exactly, and we need to optimize that.
Right, so how do we do that? What can we do?
Well, one of the big optimizations is to overlap the computation and the communication.
Okay.
So instead of waiting for the whole backward pass to finish,
Right.
we can actually start synchronizing those gradients as soon as they're available.
Okay.
It's like in that relay race, the next runner actually starts running before the previous runner has even completely stopped.
So you're squeezing more performance out by doing things at the same time.
Exactly. And another optimization, it focuses on how those gradients are actually sent.
Okay.
So it turns out it's way more efficient to send a few larger packages of gradients.
Okay.
than to send a ton of little tiny ones.
Like a full truckload is better than...
Than a half-empty truck.
Okay, yeah.
Exactly.
So it's all about making those data transfers as efficient as possible.
Exactly. And that is what we call bucketing gradients.
Bucketing grades.
And the best bucket size, well, it really depends on the hardware, and it's something people often overlook,
Hmm.
but it can make a big difference, especially when you have lots of GPUs.
Okay, so another parameter to tune to make sure everything's running as fast as possible.
Exactly. It gets pretty complex.
It does get pretty complex.
But let's bring back gradient accumulation.
Okay.
Remember from last time, that lets us simulate a bigger batch size without actually having to fit the entire batch in memory all at once.
Right, so you get the benefit of the large batch size without the memory issues.
Exactly. Now, if you were to just combine gradient accumulation and data parallelism in the most basic way, you would end up synchronizing the gradients after every single microbatch.
Oh.
But that can lead to a lot of redundant communication.
Oh, right.
It's like back and forth unnecessarily.
Yeah, so more wasted time, those runners standing around again.
Yeah, exactly. So the solution is to actually disable synchronization.
Okay.
Until you have accumulated all the gradients from all the microbatches within a step.
Right, so you're being very careful about when you're communicating.
Yes, very strategic. And in PyTorch, you can do this with model.nosync.
Okay, so we're really getting into the weeds here.
We are.
This is all very theoretical. How do we actually put this into practice? What do we do?
So let's think back to global batch size.
Okay.
Last time we learned that it's the product of your microbatch size and how many gradient accumulation steps you're doing.
Right, that equation was really helpful.
Yeah. So now with data parallelism, there's one more thing to add to that equation.
Okay.
So the updated equation for a global batch size is the microbatch size times the gradient accumulation steps times the number of data parallel instances.
Okay, which is basically how many GPUs per user.
Exactly.
So we're just factoring in the number of GPUs.
Yeah, so you might think, well, great, I can just keep adding more GPUs
Yeah.
and get to any global batch size I want.
Right.
But it's not quite that simple.
There's got to be a catch.
There is a trade-off. So
Okay.
as you increase those GPUs, yeah, you can reduce those gradient accumulation steps,
Right.
which can make training faster.
Yeah.
But at a certain point, all that communication between the GPUs, it starts to outweigh the benefits of having all those extra GPUs.
So there's like a point of diminishing returns.
Yeah, exactly. Where adding more GPUs doesn't actually speed things up as much as you would think.
Okay, so it's not just a more is always better situation.
Right, and that's where things get even more interesting. We'll talk more about that. But
Okay.
let's walk through an example of how you might actually set this up in practice.
Let's do it.
So let's say you have a target global batch size of 4 million tokens.
Okay.
And you are working with a sequence length of 4,000 tokens.
All right, so we need 1,022 samples in our batch, right?
You got it. Now, let's say the maximum local batch size that you can fit on one GPU is just 2.
Okay, so with just one GPU, you would need 512 gradient accumulation steps.
512 to hit that target global batch size.
Oof, that's a lot.
It is. But let's say you have 128 GPUs.
Okay.
You can actually keep that microbatch size at 2
Okay.
and only use 4 gradient accumulation steps.
Wow, so that is a huge speed up just from spreading out the work.
Exactly. And if you suddenly had, say, 512 GPUs, you could keep that same microbatch size and reduce those accumulation steps down to 1.
Wow, that is incredible.
Yeah, so you're training much faster.
This is amazing. But I'm just thinking, what if even one layer of our model doesn't even fit on one GPU?
That's a great question, and that brings us to the limitations of data parallelism.
Uh-oh.
But there's another technique we can use. It's called zero.
Zero.
But that's a story for next time.
Okay, cliffhanger. Can't wait to hear more about that next time.
Stay tuned. So we kind of hit a wall with data parallelism.
Yeah, a memory wall.
But I hinted that there's this other tool that we have called Zero.
Zero.
And that stands for Zero Redundancy Optimizer.
Zero Redundancy Optimizer. Okay, I like the sound of that.
So data parallelism is really great.
Yeah.
It scales training,
Uh-huh.
but it does have this kind of redundancy built into it.
Okay.
Every single GPU is storing a complete copy of all the optimizer states,
Yeah.
all the gradients, and even the model parameters themselves.
So much duplication.
It's a lot of duplication, so it's kind of like having multiple copies of the same giant puzzle spread out across the table. It's not really efficient.
Not very efficient, no.
And that's where Zero comes in.
Okay.
It partitions those different pieces, the optimizer states, the gradients, and the parameters themselves,
Okay.
across the GPUs, so each GPU only stores a fraction.
Also, it's like instead of having a complete puzzle on each GPU, They each have a piece of the puzzle.
Exactly. That's a good analogy.
Okay.
And so that reduces the memory usage significantly.
Right.
And 0 actually has different stages, each one offering a different level of partitioning.
So like levels in a video game.
Exactly. You unlock more memory savings at each level.
Okay, I'm ready to level up.
But you might introduce a little bit more communication overhead.
Okay, trade-off.
But let's start with level 1, 0, 1.
Okay.
This one focuses on partitioning the optimizer states.
Okay, the optimizer states. So those are the things that the optimizer needs.
Right. Remember the optimizer's updating the model's parameters during training,
Uh-huh.
and it's keeping track of its own states to do that?
Right, like remembering which direction to go and how much momentum it has and all that stuff.
Exactly.
To make sure it's moving in the right direction.
Precisely. So in 0, 1, we take those optimizer states.
Okay.
And we divide them up across all the GPUs.
Okay.
So each GPU only stores a portion of them. So right away, you're reducing memory usage.
Yeah, because they don't each need the full set.
Because you're no longer replicating that whole optimizer state on each GPU.
Yeah.
It's like instead of each GPU having the full set of directions,
Yeah.
they each just have like a part of the map.
Okay, I like that.
But there is a little bit of a catch.
There's always a catch.
During the forward pass, when you actually need the full set of parameters,
You're right.
you got to gather all those pieces from the different GPUs.
So there's an extra communication step there?
There is. So it's like those GPUs all need to come together
Yeah.
and quickly share their parts of the map.
Right.
Before they can continue on.
Okay.
And 0, 1 introduces something called an all-gather operation.
We'll gather.
And it happens after the optimizer step.
Uh-huh.
And that basically gathers all those updated parameters from all the GPUs.
Okay, so all gather, another one of those distributed communication things.
It is, but it's like all the GPUs are getting together
Yeah.
to assemble the whole puzzle.
Right.
And everybody has the complete picture before they move on.
Okay, so 0, 1 saves us memory by splitting up the optimizer states.
Yeah.
But it adds a little bit of communication overhead with that all gather.
Exactly. There is a little bit of a trade-off.
Right, well, what about 0, 2? Does that get even better?
So 0, 2, it takes partitioning one step further.
Okay.
It partitions not just the optimizer states,
Okay.
but also the gradients.
We're splitting up the gradients now, too.
We are.
Wow, okay.
So instead of doing that all reduce on the gradients
Yeah.
after the backward pass,
Right.
we do something a little more efficient. It's called reduce scatter.
Reduce scatter, okay.
It's a little bit complex to explain.
Okay.
But basically, it distributes those gradients in a very clever way.
Okay.
So each GPU only ends up getting the part that it needs
Wow.
for its own local optimizer step.
So it's like we're getting a lot more organized with these puzzle pieces.
We're getting smarter about it.
Yeah.
And that actually reduces both the memory usage
Okay.
and the communication overkill
Compared to 0, 1.
compared to 0, 1.
Wow.
And a lot of times 0, 2 is like the sweet spot
Okay.
because you're getting a lot of memory savings
Yeah.
without adding too much extra communication.
Awesome. All right. Well, we have to go deeper, though, right?
We do.
Just got to be 0, 3.
There is. 0, 3, also
Right.
known as fully sharded data parallelism, or FSDP.
FSDP.
That's where things get really extreme.
Extreme. Okay, what are we partitioning now?
Everything.
I knew you were going to say that.
Optimizer states, gradients, and even the model parameters themselves.
So each GPU just has a tiny, tiny piece of the whole model.
Yeah.
Wow. How does that even work?
That's where on-demand gathering comes into play.
On-demand gathering. Okay.
So during the forward and backward passes, 0, 3 only gathers the parameters it needs from other GPUs
Okay.
when it needs them for that particular layer.
So it's like each GPU is like, hey, I need that piece of the puzzle over there.
Right, and then it uses it, and then it puts it back.
It puts it back. Okay, I like that.
And so that keeps the memory footprint on each individual GPU really low.
Right. Okay.
Now, of course, all this gathering does add some communication overhead.
Right.
But the trick is to overlap it as much as possible.
Yeah, just like we were talking about before.
With the computation, just like with data parallelism.
Always got to have that efficiency in the relay race.
Exactly. So if you implement it carefully, you can actually overlap the gathering of parameters for the next layer while the current layer is doing its thing.
Okay.
So it minimizes that impact on the training speed.
Wow, that's really clever.
Yeah. So 0, 3 gives you the most memory savings.
Okay.
But you do have to be a little bit more clever
Right.
about how you manage all that communication.
Okay, so it's kind of like 0 is like different levels of,
It is.
of optimization.
Yeah.
You pick the one that's right for you.
Yeah. It depends on the size of your model, how many resources you have.
Yeah.
But it's amazing how we can train these models now.
Right.
That we couldn't have even imagined just a few years ago.
It's incredible. It really is.
It really is pushing the boundaries of what's possible.
Absolutely. But are there any limitations to 0? Is there anything it can't do? You were saying there are some limitations with 0.
Yeah, 0 is great, but it can't solve everything.
Okay.
It's really good at partitioning the weights, the gradients, the optimizer states.
Right.
But there is one thing it doesn't really address,
What's that?
and that's activations.
Oh, right, activations, those intermediate results that each layer produces.
Yeah.
Those can get really big, especially with those long sequences.
Exactly. And the memory for activations, it grows with the batch size and the sequence length.
Right.
It can be a real bottleneck for
Yeah.
these really big models, even if you are using activation recomputation.
So even with zero, you can still run into these memory problems with activations.
You can.
Why can't we just shard the activations like we do with the parameters and gradients?
It would be nice, but it's not that easy.
Okay.
So in a data parallel setup,
Uh-huh.
each GPU is working with a different micro batch of data.
Right.
So they all have different activations.
Right.
So you can't really just partition them in the same way.
Okay, so what do you do?
Well, if your activations are just too big,
Yeah.
even with zero,
Are you just stuck?
not necessarily. We just need to start thinking about other dimensions of parallelization.
Okay, other dimensions.
So we've been talking about data parallelism this whole time.
Right, where you split up the data.
Exactly. But there are other ways to divide and conquer this training process.
Like what? What else is there?
Well, one really powerful approach is model parallelism.
Model parallelism. Okay.
So instead of replicating the whole model on every GPU,
Right.
you actually split the model itself
Okay.
across multiple GPUs.
So like instead of having a complete puzzle on each GPU,
Yeah,
now each GPU has a section of the puzzle.
exact.
So we're chopping up the model.
We are chopping up the model, and this lets you train these truly massive models
Wow.
that wouldn't even fit on a single GPU, even with zero.
Okay, so model parallelism lets us deal with those just gigantic, ginormous models.
Exactly. And there are actually a few different ways to do model parallelism.
Okay, like what?
One common one is called pipeline parallelism.
Pipeline parallelism.
So you divide the model into different stages,
Okay.
and each stage gets assigned to a different GPU.
Like an assembly line.
Like an assembly line, each GPU does its part,
Right.
and then passes its output onto the next GPU.
Okay. Yeah, I like that.
This works really well for deep models,
Uh-huh.
where the computations can be kind of neatly split up into these sequential stages.
So each GPU is like a specialized worker on the assembly line.
That's a great way to put it.
Okay, cool. You said there were other types of model parallelism, though.
Yeah, another one is called tensor parallelism.
Tensor parallelism.
And that focuses on splitting up individual layers
Okay.
across multiple GPUs.
So we're breaking down those puzzle pieces even further.
We are.
So instead of splitting at the stage level,
Yeah.
we're splitting within the stage.
Exactly. So this is really useful for models with those really huge layers like you
Right.
see in some of the transformer architectures.
Okay.
So by splitting those up,
Yeah.
you reduce that memory footprint on each GPU.
This is getting really complicated.
It is.
Are there any other dimensions we need to worry about?
Well, there is one more I should mention. It's called data parallelism within model parallelism.
Data parallelism within model
It's
parallelism.
a mouthful.
Yeah.
But basically, you combine the two approaches.
Okay.
So first, you split the model across the GPUs using model parallelism.
Yeah.
And then you apply data parallelism within each of those model partitions.
So it's like having multiple assembly lines,
Yeah.
each with its own team, working on a different part of the car.
Exactly. That's a perfect analogy.
Okay.
So you're getting the benefits of both.
Of data parallelism and model parallelism.
Exactly. Really pushing the boundaries of what's possible.
Wow, it's incredible how we can just mix and match these different techniques
Yeah.
to kind of get the performance that we need.
It's like a whole toolbox.
Yeah.
And you're picking and choosing the right tool for the job.
Yeah, to fit those different models in the hardware.
Exactly. And this is still a rapidly evolving area. It's
Yeah.
a real testament to the ingenuity of all the researchers
Yeah.
and engineers who are working on this stuff.
Yeah.
They're constantly coming up with new and innovative ways
Yeah.
to solve these problems.
Yeah, so we started with this basic data parallelism.
Right.
Then we got into the memory savings with zero.
Mm-hmm.
And now we're talking about model parallelism.
It's a whole journey.
It really is.
But it's clear that parallelization is essential
Yeah.
if we want to unlock the full potential of these large language models.
It really, and it's fascinating to me how all of this is really about
Yeah.
taking these massive, massive problems
Yeah.
and breaking them down
Mm-hmm.
into these manageable pieces.
Yeah.
And then spreading them out efficiently.
Yeah, exactly.
And then orchestrating all of it
Mm-hmm.
so that we can actually train these models.
That's a great way to summarize it.
It's really cool.
And it's changing all the time.
I bet.
There's always something new to learn in this field.
That's for sure. Well, if you want to dive in even deeper,
Yeah.
we've got some great resources in the show notes.
Check them out.
Happy training, everybody. And until next time, keep on exploring the amazing world of AI. Welcome back. Last time, we did a deep dive into data parallelism.
Right.
And we explored some cool optimization techniques like overlapping gradient synchronization
Mm-hmm.
and zero.
Yeah.
But what happens when your model is so massive
Yeah.
that even sharding parameters and gradients and optimizer states isn't enough?
That's when we step into the realm of tensor parallelism and context parallelism,
Okay.
techniques designed to handle the memory demands of truly gigantic models.
Okay, so before we jump into the new stuff,
Sure.
can you quickly remind us why data parallelism alone
Yeah.
isn't enough for these massive models? We talked about zero partitioning model data, but where do we still hit a bottleneck?
The bottleneck often lies in the activation memory.
Okay,
Activations, those intermediate results produced during the forward pass, can consume a significant amount of memory,
right.
especially for large models and long sequences.
Uh-huh.
Even with zero, the sheer volume of activations can overwhelm a single GPU's memory capacity.
Right, those activations can be huge. So that's where tensor parallelism, or TP, sets in.
Exactly.
It sounds like TP takes sharding to a whole new level.
Yes.
Instead of just splitting model parameters and optimizer states like in zero,
Right.
it also tackles those memory-hungry activations.
Exactly. TP allows us to shard model parameters, gradients, optimizer states, and activations across multiple GPUs.
Okay,
Think of it like dividing a massive matrix multiplication problem among a team of workers.
okay.
Each worker handles a portion of the matrix,
Uh-huh.
reducing the memory burden on any single worker.
So if I'm picturing this correctly with TP, I could train a model with, say, 70 billion parameters.
Yeah.
By distributing those parameters and their activations across multiple GPUs?
Yes.
Is that the kind of memory saving we're talking about?
Absolutely. TP can drastically reduce the memory required per GPU,
Wow.
enabling the training of models that would be impossible to fit on a single device.
Yeah.
In the case of a 70B parameter model, TP can bring the memory requirement down to a manageable level for each GPU.
That's incredible. It seems like we're now able to scale model size without needing to scale up our hardware at the same rate.
Right.
Now I'm thinking about those transformer blocks.
Yes.
The workhorses of many of these large models.
Uh-huh.
How does TP actually work within those blocks with their feed-forward and multi-head attention layers?
Good question. In the feed-forward layers, TP uses a combination of row-wise and column-wise sharding to distribute the workload across the GPUs.
Okay.
For example, the first linear layer might use column-wise sharding, where each GPU processes a subset of the columns of the weight matrix.
Okay.
The output is then broadcasted, and an all-reduce operation is used to combine the results from all GPUs.
Okay.
The second linear layer, often row linear, restores the full hidden dimension.
So we split the matrix, process it in parallel, and then combine the results.
Exactly.
What about the multi-head attention layers? How does TP handle the attention mechanisms?
For multi-head attention, each GPU can focus on a subset of the attention heads. It's like having a team of specialists, each handling a specific aspect of the attention mechanism.
Huh.
However, there's a constraint on the degree of TP we can apply here.
Okay.
The number of attention heads needs to be divisible by the number of GPUs participated in TP.
Okay, so there are limitations. And I'm guessing all this sharding and distributing comes with some communication overhead, right? We're moving data between GPUs all the time.
You're absolutely right. That's the trade-off with TP.
Okay.
While it reduces memory usage, it introduces communication requirements.
Uh-huh.
This overhead isn't too bad when communication happens within a node,
Right.
using fast interconnects like NVLink.
Okay.
However, when we scale across multiple nodes and rely on slower network connections,
Yeah.
the communication overhead becomes more pronounced.
So finding the right balance between memory savings and communication overhead is crucial.
Yes.
It's not just about blindly maximizing parallelism. Now, we've talked about how TP helps us shard the matrix multiplications
Right.
in those attention and feed-forward layers.
Uh-huh.
But what about operations like layer norm and dropout? They seem like they would need the full hidden dimension to work correctly.
You've hit upon another key aspect of model parallelism. Operations like layer norm and dropout do indeed require the full hidden dimension.
Okay.
And that's where sequence parallelism, or SP, comes into play.
SP. So it sounds like SP is designed to complement TP.
Yes,
Is it also a sharding technique?
it is. But instead of sharding across the hidden dimension like TP-SP shards along the sequence dimension,
Okay.
this allows operations that need the full hidden dimension to operate on smaller chunks of the sequence.
Interesting. So we're strategically dividing the workload across both the hidden dimension and the sequence dimension to optimize memory usage.
Right.
Are there any special tricks involved in coordinating between these TP and SP regions?
Definitely. To manage the transitions between TP and SP regions, we use collective operations like all gather and reduce scatter.
Okay.
These operations ensure that the data is in the right place at the right time for each stage of the computation.
All gather and reduce scatter. Those sound familiar from our deep dive on Zero.
Yes.
They're powerful tools for efficient distributed training, aren't they? Could you give us a quick refresher on how they work in this context?
Of course. Imagine you have a team working on a project, each member with a piece of the puzzle.
Okay.
All gather is like having everyone bring their pieces together so that everyone has the complete picture.
Right.
Reduce scatter, on the other hand, is like distributing the pieces back to the team.
Okay.
But this time, each member only receives the pieces relevant to their specific task.
Okay, that's a helpful way to visualize it. So all gather brings everything together, and reduce scatter distributes only the necessary information. Now, I'm curious about the communication overhead of SP compared to TP.
Yes.
It seems like SP would involve more communication with those additional all-gather and reduce-scatter operations.
It might seem that way, but SP actually has an equivalent communication volume to TP.
Oh?
It's just distributed differently.
So it's not about the amount of communication, but rather how it's managed. So with SP working alongside TP,
Right.
we can push the boundaries of batch size and sequence length even further without being crippled by communication costs.
Exactly.
But even with these techniques, I imagine there's a limit to how long our sequences can be before we run into trouble.
You're right. Even with TP and SP, extremely long sequences like those found in very large language models can still exceed the memory capacity of our distributed system.
Okay.
This is where context parallelism comes into play.
Context parallelism. Okay, this is where things get really interesting. We've sharded across the hidden dimension.
Yes.
We've sharded across the sequence dimension.
Right.
What else is there to shard?
With context parallelism, we take the bold step of splitting the input sequence itself across the entire model, including the attention blocks.
Whoa, we're splitting the sequence now.
Yes.
I'm already sensing some potential challenges, especially with the attention mechanism,
Right.
which needs to consider relationships between tokens across the entire sequence.
Uh-huh.
How do we maintain that global view of the sequence when it's split across multiple GPUs?
You've identified the key challenge of context parallelism. While most modules like MLPs and layer norms handle this sequence splitting gracefully because they process each token independently,
Okay.
attention requires special handling.
Uh-huh.
It needs to be aware of the entire sequence to compute those all-important relationships between tokens.
Okay.
This is where a technique called ring attention comes into the picture.
Ring attention. Okay, I'm intrigued. It sounds like it's going to involve some clever data passing between GPUs.
Exactly. Ring attention is designed to efficiently handle the communication of key-value pairs when the sequence is split across multiple GPUs.
Uh-huh.
Think of it like a relay race where each GPU passes information to the next in a ring-like pattern.
I'm picturing a circle of GPUs, each holding the piece of the sequence passing data around.
Yes.
So each GPU processes its chunk and then shares its results with its neighbor.
That's a good way to visualize it. It's like a carefully orchestrated dance of information exchange.
Okay.
Ensuring that each GPU has the information it needs to compute the attention scores for its portion of the sequence.
But wouldn't this kind of relay race create bottlenecks?
Yes.
Some GPUs might end up waiting for others to finish their computations before they can proceed.
You've highlighted a potential issue with a naive implementation of ring attention. Because of the way the causal attention mask works, some GPUs end up with a heavier computational workload than others,
Right.
leading to imbalances and inefficiencies.
Ah, that makes sense. So how do we make this ring run smoothly and efficiently?
This is where a more sophisticated technique called zigzag ring attention comes in. It's like a smarter version of the relay race where the runners are strategically positioned to ensure a balanced workload.
Zigzag ring attention. I'm already liking the name. It sounds like it's going to involve some clever arrangement of the data.
Precisely. Instead of distributing the input tokens sequentially to the GPUs, zigzag ring attention mixes things up. It ensures that each GPU has a good mix of early and late tokens, balancing the computation and preventing those bottlenecks you mentioned.
So it's all about smart distribution. This must make a big difference in performance, right? By avoiding those bottlenecks, we can keep all the GPUs busy and avoid unnecessary waiting.
Absolutely. Zigzag ring attention leads to a much smoother and more efficient flow of information during the attention computation.
Okay.
But even with this technique, there are different ways to approach how we implement this communication and computation overlap.
So within zigzag ring attention, there are still choices to be made. I'm eager to hear about the different options and their trade-offs.
There are two main approaches, the all-gather implementation and the all-to-all or ring implementation.
Okay.
Both utilize the zigzag token distribution strategy, but differ in how they handle the communication of key-value pairs.
Okay, two flavors of zigzag ring attention. Let's break them down and see what makes them unique.
The all-gather implementation is like gathering all the puzzle pieces from everyone on the team at once.
Right.
It's simpler to implement,
Okay.
But it requires more temporary memory because each GPU needs to store all the key value pairs from all other GPUs.
So it's easier to manage, but comes with a higher memory cost. What about the all-to-all approach?
The all-to-all or ring implementation is like a well-coordinated exchange where each GPU only receives the specific pieces it needs from its neighbor in the ring.
Okay.
It's more memory efficient as each GPU only needs to store one additional chunk of data at a time.
So it's a bit more complex to coordinate, but gentler on our precious memory resources. It seems like the choice between these two implementations comes down to a trade-off between memory efficiency and implementation complexity.
Exactly. The best choice depends on the specific hardware constraints and the scale of the model we're dealing with.
This is fascinating. We've gone from sharding parameters and activations with TP and SP to splitting the sequence itself with context parallelism and these clever ring attention implementations. It's remarkable how each technique builds on the previous ones to address the challenges of training these massive models.
It truly showcases the ingenuity of the researchers in this field. They're constantly pushing the boundaries of what's possible, devising creative solutions to overcome limitations and enable us to train increasingly powerful AI models.
It's like an ongoing game of innovation leapfrog, with each new technique propelling us further into the realm of massive-scale AI. Before we move on, I want to make sure I have a crystal clear understanding of how TP and SP work together. Could we walk through a specific example of how the activations change shape as they flow through a transformer block with both TP and SP applied? I think it would really solidify my understanding of this intricate dance of dimensions.
Absolutely. Let's take a transformer block with a hidden dimension of h and a sequence length of h as our example.
Okay, H for hidden dimension and H for sequence length. I'm ready to follow along.
Great. So when we enter the TP region, specifically the first linear layer, which is often column linear, the hidden dimension gets sharded. If we have two GPUs for TP, each GPU will process H2 of the hidden dimension. However, the sequence length remains untouched at this point. Each GPU sees the full sequence of H.
So we've sliced the hidden dimension in half, but the sequence length remains intact. Got it. What happens next?
The activation function, like GLU, is applied independently on each GPU. This doesn't change the shape of the activations. Then we move to the second linear layer, which is usually row linear. This layer restores the hidden dimension to its full size H. So after this layer, each GPU has activations of shape BXSXH, where B is the batch size.
Okay, so we split the hidden dimension, processed each part, and then brought it back together. So we're back to the full hidden dimension and the full sequence length.
Precisely. But remember, we're also applying SP, which shards along the sequence dimension. Before these activations move to the next SP region, we need to scatter them. We reduce along the hidden dimension to ensure correctness with the row linear layer and scatter them along the sequence dimension.
So each GPU ends up with a chunk of the sequence, let's say S2, if we have two GPUs for SP, but with the full hidden dimension of H.
Exactly. Now these activations of shape BXS2XH enter the SP region. Here, operations like layer norm, which require the full hidden dimension, can be applied independently on each GPU to their respective portion of the sequence.
Wow, this is intricate. It's amazing how these techniques work together to optimize memory without messing up the computations. It's like a perfectly synchronized dance of data across these different dimensions.
That's a great way to put it. It's a testament to the cleverness of the algorithms and the careful engineering that goes into making these large-scale models trainable. Speaking of cleverness, remember how we talked about layer norm and TP training, not needing an all-reduce for gradient synchronization?
Oh yeah, that was a pretty cool detail. Can you remind us why that is again?
It's because each TP rank sees the same activations after the all-gather operation in the forward pass. This ensures that the layer norm weights stay synchronized naturally during the backward pass, eliminating the need for that explicit gradient synchronization step.
So layer norm gets a free pass. That's pretty neat. But what about dropout? Does it get the same special treatment in TP training?
Dropout, while less common in large language models these days, can still be relevant in some architectures. For dropout to work correctly in TP, we need to make sure that the random seed used for dropping out neurons is synchronized across all TP ranks. Otherwise, we'd end up with different neurons being dropped out on different GPUs, leading to inconsistencies and incorrect results.
That makes sense. We want to maintain deterministic behavior even when we're splitting things up across multiple GPUs. It's amazing how much thought goes into making sure these techniques work correctly in a distributed setting.
It's a complex challenge, but it's essential to get these details right to ensure the reliability and accuracy of our models, especially at such a large scale.
Okay, we've covered a lot of ground here. We've got tensor parallelism splitting things along the hidden dimension sequence, parallelism working its magic on the sequence dimension, and context parallelism taking the bold step of splitting the sequence itself. It's like a multi-dimensional game of Tetris optimizing memory usage at every turn.
I like that analogy. And just like in Tetris, we need to carefully consider the trade-offs involved. Each of these techniques comes with its own set of advantages and disadvantages.
Right. We talked about the communication overhead associated with TP, especially when scaling across multiple nodes. What are some other key trade-offs we need to keep in mind when choosing how to parallelize our training process?
One of the biggest trade-offs is between computational efficiency and memory availability. As we increase the degree of parallelism with TPSP or context parallelism, we generally reduce the memory requirements per GPU. But this often comes at the cost of reduced throughput, meaning it might take longer to train the model.
So it's a balancing act. We want to maximize memory efficiency to handle those massive models, but we also want to keep the training process as fast as possible. How do we decide where to strike that balance?
It's not always about maximizing parallelism. We need to consider the communication overhead, the characteristics of our hardware, and the specific requirements of our model. Sometimes it might even make sense to combine different parallelism techniques to strike the best balance.
So it's not a one-size-fits-all approach. It's about carefully analyzing our resources and tailoring our parallelism strategy to achieve the best results. It sounds like there's quite an art to this. What tools or techniques can help us navigate these complex decisions?
You're right, there's definitely an art to it. Fortunately, there are tools and libraries like MegatronLM and DeepSpeed that provide the building blocks and the flexibility to experiment with different parallelism configurations. These tools allow us to find the optimal settings for our specific training setup.
It's like having a toolbox filled with powerful instruments, each designed for a specific purpose. We as AI practitioners need to become skilled artisans, understanding how to use these tools effectively to sculpt our training process. But before we get too carried away with the artistic side of things, let's come back to the practicalities of TP and SP. You mentioned a table earlier that summarized how the shape of the activations changes as they flow through a transformer block with both TP and NV applied. I think revisiting that table would be really helpful for our listeners to solidify their understanding.
Absolutely. That table provides a handy reference for keeping track of how those dimensions are being manipulated at each stage of the conversation. Are you ready to dive back into the table?
Definitely. Let's break it down step by step and make sure we have a clear picture of how those dimensions are being sliced and diced.
Great. So let's start at the beginning with the embedding layer. In a standard setup, the embedding layer produces activations of shape, SBSXH, where B is the bat size, is the sequence link, and H is the hidden dimension. Now, with TP and SP in the mix, things get a bit more intricate.
Okay, I'm ready to follow along. What happens to those dimensions in the embedding layer when TP and SP are applied?
The embedding layer itself can be sharded using row-wise TP. This means that each GPU will process a portion of the vocabulary and produce a partial embedding matrix. To get the full embedding for each token, we would normally perform an all-gather operation. However, because we're also using SP, we use a reduce scatter operation instead.
So instead of gathering the full embedding matrix on each GPU, we're reducing it along the vocabulary dimension and then scattering it along the sequence dimension. It's like we're strategically distributing those embedding vectors right from the start.
Exactly. So after the embedding layer, each GPU ends up with activations of SHEP BXXH, where N is the number of GPUs. We've already split the sequence dimension in the embedding layer.
Okay, that makes sense. We're starting with a sharded representation of the sequence. What happens next as we move into the TP region, specifically the first linear layer, which you mentioned is often column linear?
Now, in the column linear layer, the hidden dimension H gets sharded, but the sequence dimensions remains intact. Let's say we have two GPUs for TP. Each GPU will process half of the hidden dimension H2, but still see the entire sequence length.
Got it. So we're slicing along the hidden dimension, but keeping the sequence length intact at this point. What happens in the next layer, the row linear layer?
In the row linear layer, we restore the hidden dimension to its full size. Each GPU now has activations of shape BXXXH, but remember we're using SP, so we immediately perform a reduce scatter operation. We reduce along the hidden dimension, which ensures correctness with the row linear operation, and scatter the results along the sequence dimension.
So we're back to splitting the sequence dimension after briefly having the full hidden dimension available. It's like we're weaving these dimensions together, carefully managing where the splits occur to optimize memory usage.
Precisely. After the reduce scalar operation, each GPU holds activations of shape BXSXH. These activations are then fed into the SP region, where operations like layer norm, which require the full hidden dimension, can be applied independently on each GPU to their respective chunk of the sequence.
This entire process is like a meticulously choreographed dance of data. It's incredible how TP and SP work in harmony to manage memory while preserving the computational integrity of the body. It's clear that a lot of thought and ingenuity have gone into designing these techniques.
Absolutely. And as models continue to grow, these innovations in model parallelism will become even more crucial for pushing the boundaries of what's possible with AI. But before we wrap up our discussion of TP and SP, there's one more important aspect I'd like to touch on.
Okay, I'm all ears. What else do we need to know about this dynamic duo of TP and SP?
It's important to remember that the choice of how to split the hidden dimension and the sequence dimension with TP and SP depends on a variety of factors. The size of the model, the hardware we're using, and even the specific task we're trying to solve can all influence our decisions.
So there's no one-size-fits-all approach. It sounds like finding the right balance is key to maximizing performance.
Exactly. We need to consider the communication overhead, the memory capacity of our GPUs, and the computational efficiency of different splitting strategies. It's like finding the perfect recipe for our specific training scenario.
That makes perfect sense. It's not just about blindly maximizing parallelism. It's about carefully considering all the factors at play and tailoring our approach to achieve the best possible results. It sounds like there's a real art to finding that sweet spot
Yeah,
where memory efficiency and computational speed and communication overhead all harmonize.
right.
Now, shifting gears a bit,
Sure.
we've focused intensely on the training side of things.
Yeah.
I'm curious about the implications of these parallelism techniques
Mm-hmm.
for deploying these massive models for inference.
Right.
How do TPSP and context parallelism affect the process of actually using these models
Yeah, good question.
in real-world applications?
That's a great point. Deployment is a crucial aspect of the AI lifecycle,
Right.
and these parallelism techniques can play a significant role in optimizing inference as well.
Okay.
While the specifics might differ from training,
Uh-huh.
the core principles of splitting and distributing the workload can be applied to make these models run efficiently on various hardware platforms.
So could we use TP to split a model across multiple GPUs or even specialized AI accelerators
Yes.
during inference? Would that help reduce latency and improve throughput, especially for applications where speed is critical?
Absolutely. For real-time applications like chatbots or language translation,
Uh-huh.
where responsiveness is paramount,
Right.
using TP for inference can be incredibly beneficial.
Okay.
It allows us to leverage the parallel processing power of multiple devices to accelerate the inference process.
And with the rise of edge computing, where we're seeing AI models deployed on devices with limited resources,
Right.
techniques like TP and SP become even more important for enabling these powerful models to run efficiently on less powerful hardware.
Exactly. The ability to efficiently distribute a model across multiple devices or even partition it to run on a single device with limited memory
Right.
is essential for bringing the power of these large models to a wider range of applications and platforms.
So it's not just about training these massive models, it's about making them accessible and usable
Yes.
in a wide range of real-world scenarios, from powerful cloud servers to resource-constrained edge devices. That's really exciting.
It is.
It feels like we're opening up a whole new world of possibilities for AI applications.
I agree. And as hardware continues to evolve and new types of AI accelerators emerge,
Uh-huh.
these parallelism techniques will become even more sophisticated and crucial for unlocking the full potential of these large-scale AI models.
It's amazing to see how these innovations are driving the progress of AI,
Yeah,
both in terms of model capabilities and the breadth of applications. We've covered so much ground in this deep dive,
we have.
from the fundamentals of data parallelism to the intricacies of tensor parallelism, sequence parallelism, and context parallelism.
Yeah, it's been a great discussion.
It's been a whirlwind tour of cutting-edge techniques for training and deploying truly massive AI models.
It has been quite a journey. We've explored the challenges of scaling AI models to unprecedented sizes and the ingenious solutions that researchers and engineers have developed to overcome these obstacles.
And for our listeners, I hope this deep dive has provided valuable insights into the world of large-scale AI and the incredible innovation happening in this field.
I hope so too. These techniques are shaping the future of AI, enabling us to build and deploy ever more powerful and capable models that have the potential to revolutionize countless industries and aspects of our lives.
Well, on that note of anticipation for the future of AI, I think it's time to wrap up this deep dive. Thank you so much for joining us today and sharing your expertise on these fascinating techniques.
It was my pleasure. It's always exciting to discuss these advancements and see the enthusiasm for pushing the boundaries of what's possible with AI.
And a huge thank you to all our listeners for joining us on this exploration of model parallelism. We'll see you next time for another deep dive into the fascinating world of AI. Welcome back to another deep dive. Last time we laid the groundwork for how to train massive language models, covering data parallelism, tensor parallelism, sequence parallelism, and context parallelism, and even ring attention.
Oh, wow. That's a That's a lot of parallelism.
Haha, it is, yeah. Today we're going even deeper, diving into pipeline parallelism,
Okay.
which is a crucial technique for distributing model training across multiple GPUs.
Yeah, pipeline parallelism is it's really all about efficiency, right?
Okay,
By splitting a model's layers across multiple GPUs and creating a computational pipeline, we can tackle these massive models that simply wouldn't fit on a single GPU.
so instead of like replicating the entire model on each GPU, we're dividing the workload,
Exactly.
with each GPU handling a specific stage of the model's processing. That sounds like a really smart way to distribute the computational burden, but are we just like shifting the bottleneck?
That is a great question, and that's where things can get a little tricky. While pipeline parallelism can significantly reduce the amount of data that each GPU needs to communicate at once, it does introduce a new challenge,
Uh-oh.
which we call the bubble problem.
The bubble problem.
Yeah, the bubble problem. So imagine a four-stage pipeline, right?
Okay.
The first GPU completes its forward pass, but then it just sits there idle, waiting for the other three stages to finish
Oh, okay.
before it can start the next batch of data. This idle time, this waiting time, that's the bubble.
Okay, so as we add more stages, does this bubble grow?
Exactly, yeah. As we add more stages, this bubble grows, and that reduces our overall efficiency.
So it's like an air bubble in a real pipeline, disrupting the smooth flow of data. Is there a way to like quantify this bubble effect?
Absolutely. We can define the bubble mathematically. It's essentially the difference between the total time taken for a batch to pass through the pipeline and the ideal time if there were no idle periods. So the larger the bubble, the greater the inefficiency.
Okay, I'm starting to get it. So how do we like tackle this bubble? How do we optimize the flow of computations in a pipeline parallelism setup?
Well, one approach is to use some clever scheduling schemes. Instead of waiting for all the forward passes to complete before starting the backward passes, we can overlap them.
So we're kind of interweaving the forward and backward passes to make better use of those idle GPUs.
Exactly, yeah. There are actually several different pipeline parallelism schemes that we can use, each with its own pros and cons. The simplest one is called all forward, all backward, or AFAB.
AFAB, okay. That sounds pretty straightforward. What's the catch?
Well, in AFAB, we complete all the forward passes sequentially, followed by all the backward passes.
Okay.
So it's pretty easy to implement, but it can lead to a memory bottleneck because we have to store all the activations from the forward passes until the backward pass, which can be a huge drain on memory, especially for large models.
Ah, so it's like trying to cram a massive data set into limited GPU memory. Not very efficient.
Exactly.
Is there a way to manage this memory explosion?
Yeah, so there's another scheme that addresses this memory issue called one forward, one backward, or 1F1B. Instead of waiting for all the forward passes, we start a backward pass as soon as the first stage completes its forward pass.
Okay.
So we're overlapping them a little bit. This reduces the amount of activation data that we need to store at any given time.
So we're trading memory efficiency for a bit more complexity?
Exactly.
1F1B commonly used?
Yeah, actually it is. It's the approach that's used in Llama 3.1.
Oh, wow. Okay.
So this scheme demonstrates a conscious decision to prioritize memory efficiency, even at the cost of increased scheduling complexity.
Interesting. So choosing a scheduling scheme seems to always involve a trade-off between implementation complexity and memory management. Are there other schemes out there beyond AFAB and 1F1B?
There are, yeah. Interleaved stages is another technique, offers a different approach to minimizing the bubble.
Okay.
Instead of neatly dividing the model layers across GPUs, we interleave them.
So instead of layers 1 to 4 on GPU 1 and then 5 to 8 on GPU 2, we might mix them up.
Precisely. This interleaving allows for a tighter overlap between forward and backward passes, which further reduces the bubble size. But of course, there's a trade-off.
I'm guessing this interleaving introduces more frequent communication between the GPUs because the data needs to like jump around more.
Exactly. Finding the right balance between minimizing the bubble and managing communication costs is key to optimizing pipeline parallelism.
Sounds like a delicate dance.
It is.
Are there any other like really advanced techniques that push the boundaries even further?
There are some really cutting-edge approaches out there, like zero bubble and dual pipe.
Oh, I've heard of those.
Yeah, zero bubble breaks down computations into even finer-grained operations, allowing for incredibly precise scheduling to minimize idle time. And then dual pipe, which is used in DeepSeek v3, takes this concept further by creating two streams of data flowing in opposite directions through the pipeline.
Wow, these techniques sound incredibly sophisticated. Are they commonly used in large language model training?
They're gaining traction as researchers continue to push the limits of model size and training speed. These advanced techniques highlight the constant innovation in this field.
Always striving for greater efficiency.
Exactly.
So we've got this spectrum of pipeline parallelism schemes, each with its own unique approach to managing that bubble and communication costs. But how do we choose the right scheme for a specific model and hardware setup?
That's a great question, and it leads us into the next layer of this discussion, because choosing the right pipeline parallelism scheme is only one piece of the puzzle. We need to consider the broader context of available resources, model architecture, and our training goals.
Okay, I'm ready to dive deeper. Let's explore those factors and see how they influence our choices in pipeline parallelism and beyond.
Sounds good. So choosing the optimal pipeline parallelism strategy is just the tip of the iceberg, right? We need to consider the entire landscape of parallelism techniques to efficiently train these massive language models.
So it's not just about picking one technique, but rather orchestrating a symphony of parallelism strategies all working together in harmony.
Exactly. It's about understanding the interplay between different techniques and selecting the best combination for our specific needs.
Okay, let's map out this landscape a bit.
Sure.
We've talked about data parallelism, tensor parallelism, sequence parallelism, and now pipeline parallelism. How do these all work together?
Think of it like a toolbox. Each parallelism technique offers a unique way to distribute the computations and manage resources.
Okay.
Pipeline parallelism excels at reducing communication bandwidth between stages, but it introduces that bubble problem that we talked about.
Right, and we discussed different schemes like 1F1B or interleaved stages trying to mitigate that bubble, but where do techniques like data parallelism and tensor parallelism fit into this pipeline?
They play a crucial role in how we distribute data and computations across our GPUs. Data parallelism focuses on processing different batches of data in parallel, while tensor parallelism shards the model's parameters and activations across multiple GPUs.
So we can imagine data parallelism working alongside pipeline parallelism. Each stage in the pipeline might be further parallelized using data parallelism to process even larger batches of data.
Exactly. And tensor parallelism can be applied within each stage as well, further distributing that computational load. We can even combine tensor parallelism with sequence parallelism,
Oh, right.
which divides the processing of sequences across GPUs, allowing us to handle longer sequences efficiently.
It's getting complicated. We've got these different dimensions of parallelism all interacting and overlapping. It feels like there's a combinatorial explosion of possibilities.
There is, and that's why choosing the optimal training configuration is so challenging.
And fascinating.
Yes, and fascinating. We need to consider not only the individual strengths and weaknesses of each technique, but also how they interact, how they complement each other.
So it's not just about throwing more GPUs at the problem, but strategically leveraging these techniques to maximize efficiency. What are some of the guiding principles when navigating this complex landscape?
One really important consideration is the type of model that we're training. For models with billions of parameters but relatively short sequences, a combination of data parallelism and tensor parallelism might be enough. We can use techniques like 0-3 to partition the model weights and optimizer states across GPUs, minimizing memory redundancy.
0-3, yeah, we touched on that briefly, right, when we were comparing it to pipeline parallelism.
Exactly. It's a powerful technique for reducing memory requirements and enabling us to train larger models.
Okay.
While pipeline parallelism divides the model by layer, 0-3 partitions model weights across GPUs. They're both aiming to distribute the model, but they take different approaches.
So pipeline parallelism focuses on creating that computational pipeline, while ZR03 focuses on minimizing memory redundancy. What are the trade-offs between these two approaches?
Well, pipeline parallelism can be more communication efficient for models with really giga architectures, but it introduces the bubble problem. ZR03, on the other hand, avoids the bubble, but it involves more frequent communication of weights during training.
The classic trade-off between communication frequency and computational efficiency. It seems like there's no clear winner, and the optimal choice just depends on the specific scenario.
Exactly. And as models become even larger and more complex, like those with hundreds of billions or even trillions of parameters, we often need to combine multiple parallelism techniques to effectively distribute the workload.
So we might use pipeline parallelism to divide the model across multiple nodes, with each node further leveraging data parallelism and tensor parallelism to handle the computations within its stage. It's like a hierarchical structure, optimizing data flow based on the speed and bandwidth of the connections.
Exactly. We're building this sophisticated communication hierarchy, strategically leveraging different parallelism strategies based on their strengths and limitations. And there are even more specialized techniques like context parallelism and expert parallelism that address specific challenges.
Context parallelism that was designed for handling those extremely long sequences, right? We see those in some of the modern language models. It shards activations along the sequence dimension, enabling us to work with sequences that might be too large to fit in memory otherwise. parallelized.
Exactly. And techniques like ring attention can further optimize communication within context parallelism, minimizing the overhead of sharing information across the distributed activations.
And what about expert parallelism? That one's still a bit fuzzy for me.
Expert parallelism, or EP, is specifically designed for mixture of experts models.
MOE.
Yeah, MOE, where we have multiple specialized experts within each layer handling different types of input. EP allows us to distribute these experts across different GPUs, enabling us to scale MOE models to incredible sizes.
So it's like having a team of specialists, each with their own dedicated processing unit, tackling different aspects of the input data. Sounds very efficient.
It is, but it's important to remember that EP alone only addresses the expert distribution. We need to combine it with other techniques like data parallelism to efficiently process the input batches and manage the overall data flow.
Okay, it's all starting to come together now. We've got this pool box of parallelism techniques, each addressing specific challenges and offering unique advantages. The art lies in selecting the right combination and orchestrating them to work in harmony.
That's the essence of distributed training for large language models. It's a dance between understanding the intricacies of our models, the capabilities of our hardware, and the demands of our training goals.
It sounds like this dance is constantly evolving as researchers push the boundaries of what's possible. But let's shift gears for a moment. Assuming we've mapped out our parallelism strategy, how do we actually go about choosing the optimal configuration for a specific training run? What are the key factors we need to consider? So we've explored this vast landscape of parallelism techniques, and we've seen how pipeline parallelism, data parallelism, tensor parallelism, sequence parallelism, even context parallelism and expert parallelism all play unique roles in distributing the workload and tackling those challenges of training these massive language models.
It's like assembling a team of specialized experts,
Right.
each with their strengths and weaknesses. And the art is in understanding those nuances and how to orchestrate them, how to get them to work together seamlessly.
But how do we move from this high-level understanding to actually configuring a training run? Where do we even begin?
Well, the first step is actually pretty straightforward.
Okay.
Can we fit a single training step into memory? We need to make sure that even a single instance of our model, along with all the necessary optimizer states and activations, can reside on our available GPUs.
So before we even think about parallelism, we need to make sure our hardware can handle the basic memory requirements.
Exactly.
What if we're working with limited resources? What if our model, even just one instance, is too big for our GPUs?
That's where things get interesting. We can employ techniques like activation recomputation,
Okay.
where we just recalculate activations during the backward pass instead of storing them, so we're trading compute for memory savings. Another powerful tool is gradient accumulation, which allows us to simulate larger batch sizes by accumulating gradients over multiple mini-batches.
So we're essentially stretching our resources, right? Employing these clever tricks to overcome the memory limitations. But assuming we've managed to fit our model into memory, what's the next step in configuring our training run?
Then we need to think about the global batch size.
Okay.
This determines how much data we process in each training step and directly impacts the training speed and efficiency.
Right, the batch size, that's a crucial knob to tune, right? Balancing the speed of the training with the resource constraints. How do we determine the optimal batch size for a specific setup?
Well, there are a few things to consider. If we have ample GPU memory and communication bandwidth isn't a bottleneck, we can aim for a larger global batch size, which often leads to faster training. And we can achieve this by scaling up data parallelism or using gradient accumulation.
So if we're lucky enough to be in a GPU-rich scenario,
Yeah.
we can push for those larger batches and potentially accelerate training. But what if we're working with more limited resources, a GPU-poor scenario?
Right. Well, then we might need to decrease that global batch size to fit within our memory constraints. Reducing data parallelism or adjusting gradient accumulation can help us achieve that balance. And for models with long sequences, adjusting context parallelism can further optimize memory usage.
Okay, so we fit the model into memory, we fine-tune the batch size. What's the final piece of the puzzle?
Optimizing for training throughput. We want our GPUs working as efficiently as possible, crunching through the data, updating the model weights at the fastest possible rate.
Throughput is king.
Exactly. So how do we squeeze the most performance out of our hardware? Well, if memory and communication aren't bottlenecks, we can scale up tensor parallelism within a node,
Okay.
minimizing the need for other, potentially more communication-intensive parallelism techniques. Increasing data parallelism with 0.3 while maintaining our target batch size can also significantly boost throughput.
So we're pushing different levers, strategic balancing parallelism strategies, to maximize the efficiency of our training pipeline.
Exactly. And as data parallelism communication starts to become a bottleneck, we can transition to pipeline parallelism, distributing the model across multiple nodes, alleviating some of that pressure.
So it's like a dynamic process, constantly evaluating and adjusting our parallelism strategy based on performance feedback.
Exactly.
The goal is to find that sweet spot where all of our resources are humming along in perfect harmony. Well, I think we've covered a lot of ground in this deep dive.
We have.
From understanding the fundamentals of pipeline parallelism to navigating the complex interplay of all these different parallelism strategies. We've gained, I think, a really deep appreciation for the challenges and innovations involved in training these massive language models that are really reshaping our world.
And it doesn't end here. Research in parallelism for large language models is a rapidly evolving field, with new techniques and optimizations emerging all the time.
Right.
As models continue to grow in size and complexity, the demand for efficient and scalable training methods will only intensify.
So as you continue exploring this fascinating world of large language models, remember the intricate dance of parallelism that makes it all possible?
Exactly.
Think about the strategic decisions involved in distributing those billions of parameters,
Yes.
managing communication bottlenecks, optimizing for speed and efficiency.
And keep in mind that there's no one-size-fits-all solution.
Right?
The optimal approach depends on a delicate balance of factors: the model architecture, the available hardware, the desired training speed, and even the characteristics of the data itself.
And above all, stay curious.
Yes.
Dive deep into the research, experiment with different techniques, and contribute to this incredible evolution of this exciting field.
Until next time, keep exploring, keep learning, and keep pushing the boundaries of what's possible with large language models.
This is The Deep Dive, signing off. Welcome to The Deep Dive. Today, we're going to dive deep into GPUs. We're not just going to talk about what they are, but how to really get the most out of them, like how to optimize them for, maximum performance. We're going way beyond the basics, like stuff that really separates, the casual user from a true expert, optimization expert.
Yeah, exactly. And to do that, we're going to break down the whole structure of GPUs. We'll look at kernel optimization techniques, and even some revolutionary approaches like flash attention, which are, really changing things, especially for AI.
Sounds pretty good. So maybe we should just start with the basics of GPU architecture. What makes them so unique and powerful?
Well, GPUs are designed for parallel processing, right? And it's their hierarchical structure that really makes this possible. You can think of it kind of like an army, with streaming multiprocessors, or SMs, acting as the generals. And each SM, it commands this battalion of cores, kind of like the soldiers, carrying out the instructions.
Okay, so an army needs logistics, right? So GPUs have this multi-tiered memory system.
Exactly. Each core has its own registers, which is the fastest memory, but it has, limited capacity, like a soldier's backpack, only holding essentials.
And then we have shared memory and L1 cache. That's like a step up in the hierarchy.
Yeah, thinking that like a shed tent, maybe for a squad. Faster to access than going all the way back to the central supply depot, which is global memory in this analogy. And this hierarchy allows for this, massive parallel processing, so many tasks happening all at the same time.
Okay, so we got this army of cores all ready for action. So how do we actually tell them what to do?
Well, that's where kernels come in. Kernels are these pieces of code that are executed on the individual cores, like specific instructions, to each soldier. We use languages like CUDA or Triton to actually write those instructions.
Okay, so the host code, which is running on the CPU, it prepares the data, right? So it's like the command center sending orders to the soups on the ground. The GPU.
Exactly. That's a great way to think about it. The host code sends these orders in the form of data and kernels to the GPU for processing.
And then these kernels, they're organized into warps and blocks, which makes things even more efficient, right? So what exactly are those?
So warps are groups of 32 threads, like squads of soldiers, working together. And blocks are larger groups of those warps, so kind of like platoons carrying out a coordinated mission. And organizing them like this into warps and blocks is it's really important for optimizing performance because it dictates how the work is shared and executed across all those cores.
Interesting. So understanding how things are organized like this is really key to optimization.
It's like a military strategist, considering the battlefield, deploying troops effectively, writing efficient kernels. You have to understand these constraints.
Right. So when it comes to actually writing the kernels, are there different tools for this? Like each with their own pros and cons?
Yeah, there are. You have PyTorch, which is, very user-friendly, but maybe not the fastest. And then there's Torch.compile, which offers a good balance of ease of use and speed.
And if you really want peak performance, there's Triton and CUDA.
Exactly. It's about choosing the right tool for the job. A simple hammer is fine for basic tasks, but for something more demanding, you need, specialized tools.
Right. So let's say we've, chosen our weapon and crafted our kernel. How do we make sure it runs as efficiently as possible on this, hierarchical battlefield?
Well, one of the most important things is memory access optimization. You want to minimize, trips back and forth to that central supply depot, the global memory, because it's the slowest part.
Okay, so how do we actually do that? I've heard of this term memory coalescing.
Memory coalescing is essential. Yeah, it's like imagine soldiers, right? All grabbing supplies, but in an orderly line, each one accessing consecutive memory locations. This allowed the GPU to grab data in larger chunks, so it reduces latency.
Okay, that makes sense. But how much of a difference does it actually make, like in the real world?
Oh, in some cases, memory coalescing can boost memory throughput by like 10 times. Let's say, for example, you're doing matrix multiplication. This is super common in deep learning. Just by changing how threads access the data, you can get massive performance gains.
Wow. 10 times faster just by being smart about memory access. That's pretty amazing. So what other tricks can we use?
Well, another powerful technique is tiling. You know how we talked about soldiers storing supplies in a shared tent? So tiling uses the faster shared memory to store and reuse data. It means we don't have to keep going back to that slower global memory.
So instead of those constant trips back to the central depot, they have a local cache.
Yeah, precisely. And this can lead to even more performance gains, sometimes more than 40%, reaching speeds up to 6.6 TFL opsos. That's, trillions of floating point operations every second.
Wow, those are crazy speeds. Are there any other memory optimization techniques?
Yeah, we have threat coarsening. We merge multiple threads to reduce shared memory access, like one soldier carrying multiple supplies instead of many soldiers each carrying one. So, less traffic going in and out of the shared memory.
Right, less congestion means fast operations. Makes sense.
And finally, there's minimizing control divergence. Remember how warps execute instructions in lockstep? Control divergence happens when threads within a warp start, following different paths, like soldiers getting separated, having to wait for each other.
So keeping them all in sync is really key.
Exactly. Avoiding those unnecessary branches in the code can really help prevent this and keep things running smoothly. Okay, now before we move on, there's another concept I want to touch on, and that's fused kernels.
Okay, fused kernels. Sounds interesting. Tell me more.
So think of it like completing multiple tasks in one trip, instead of going back and forth, between the base and the battlefield.
So you combine multiple kernels into one, like a super kernel?
Yeah, exactly, streamlining everything. And this reduces the communication overhead between the CPU and GPU, right? Which makes things run faster, especially for more complex tasks.
Yeah, I just see how that'd be super beneficial. So where are these fused kernels, really used?
Well, one area is transformer models, especially optimizing layer normalization. But before we go into that, let's talk about the star of the show today, flash attention.
Yeah, flash attention. I've heard it's pretty revolutionary, so what makes it so special?
It really is. Flash attention is a game changer. It's all about how it handles memory. See, traditional attention mechanisms need to make this like attention matrix, which can be massive, especially with long sequences, right? And it just puts a strain on memory bandwidth, creates a bottleneck.
So flash attention bypasses that bottleneck. How does it do that?
It does. It's really ingenious. Instead of building the whole attention matrix, it computes the information in small chunks right within the faster shared memory. So it uses less memory and speeds up computation at the same time.
Wow, win-win. No wonder it's become so popular. And what about flash attention 2 and 3? Are they even more revolutionary?
Well, Flash Attention 1 was, the big breakthrough. Versions 2 and 3 really focused on making it work even better on different hardware. Flash Attention 2 minimized non-matmel operations. And version 3, it was tailored to the latest NVIDIA Hopper architecture, especially for, FP8 and Tensor Core support.
FP8, that sounds like a whole other level of optimization.
Yeah, it is. It involves using lower precision formats for calculations, which can really speed things up. And actually, we're going to delve into that and the whole world of mixed precision training in the next part of our deep dive. Welcome back. So, as promised, let's get into mixed precision training. It's a technique that can really boost performance on GPUs.
Okay, so it's like we're fine-tuning the ammunition for our GPU soldiers, making them even more efficient in battle.
That's a great analogy. So the standard in deep learning has always been using FP32, which is single precision floating point format. For numerical precision, it means that each number uses 32 bits of memory.
32 bits for every number. That seems like a lot, especially with these huge models with millions or billions of parameters.
Exactly, and that's where mixed precision train comes in. We use lower precision formats like FP16, BF16, or even FP8 for some of the calculations.
So we're kind of like using smaller units of measurement, trading a bit of accuracy for speed.
Exactly. It's like using a lower resolution picture. You might lose some detail, but it uses less space and loads faster, right?
Right, that makes sense. But wouldn't use have lower precision, make our models less accurate?
Yeah, that's the challenge. That's why it's called mixed precision. You can't just switch everything to lower precision without, using some clever tricks.
Okay, so what are those tricks? How do we make sure we're not sacrificing too much accuracy?
Well, let's start with FP16 and BF16 training. Those are the most common lower precision formats. One important technique is to keep an FP32 copy of the weights. It's like having this master blueprint in high resolution, even if we're working with a lower res model for some of the operations.
So it's like our reference point to make sure we don't drift too far from the original, more precise values.
Right, and then there's loss scaling. Imagine you're amplifying a weak signal so it's easier to process. So loss scaling prevents the gradients from getting too small, which can be a problem with lower precision.
And I'm guessing the last technique, accumulation, is all about improving the overall accuracy, right?
You got it. Accumulation basically means summing up the intermediate results in F to 32 before we convert them back to the lower precision format. Like taking multiple measurements with a less precise tool and then averaging them to get a more accurate reading.
Clever. So with FP16 and BF16, we get more speed without losing too much accuracy. But you mentioned FP8 early. Is that even faster?
FP8 is faster, yeah, but it's also a lot more challenging to use. You need even more sophisticated techniques to make it stable.
Yeah, I can imagine. Using even lower precision must make it even more likely to run into overflow and underflow issues?
Exactly. One promising technique to address this is per tile range normalization. It basically normalizes values within small chunks of data, so it's less sensitive to outliers.
So it's like having a bunch of carefully calibrated measuring tools for different parts in the data.
Exactly. And a good example of large-scale FP8 training is DeepSeek V3. They trained a massive model using FP8 and got really impressive results.
That's pretty cool. It sounds like FP8 is still in its early stages, but it has huge potential, right?
Absolutely. It's still experimental, but it's probably going to become the standard soon, maybe even surpassing BF16. And who knows, we might even see FP4 training in the future.
Wow, FP4, that would be amazing. Okay, so we've covered so much already, from GPU architecture and memory optimization to kernels, flash attention, and mixed precision training. But before we wrap up, I want to go back and look more closely at how we actually optimize those kernels, especially when it comes to memory access. It's one thing to understand the concepts, but seeing how it's applied in practice would be really helpful.
I agree. Let's go back to some of those key memory access optimization techniques and break down how they work in real-world examples, like with matrix multiplication.
All right, let's get into the details of kernel optimization. We talked about memory coalescing before, but how does it actually work, say, with matrix multiplication?
Matrix multiplication is a great example, yeah, because it's so fundamental to deep learning. If you just implemented it naively, the threads might be accessing memory in a really scattered way. Imagine soldiers running all over the place, grabbing supplies from random spots. It'd be super slow and inefficient.
Yeah, definitely not the organized efficiency we want. So how does memory coalescing bring order to that chaos?
Well, with memory coalescing, we make sure that threads in a warp are accessing memory locations that are right next to each other, like those soldiers, all lining up to get their supplies in order. It minimizes wasted movement, and that makes the whole process much faster.
So it's about making the access pattern match how the GPU actually fetches data.
Exactly. And the best part is you often just need small tweaks in the code, like how you calculate the memory addresses, and that can make a huge difference.
You said we could see a tenfold increase in throughput, right? That's a massive gain for a relatively small change.
Absolutely. And those gains mean faster execution time for your deep learning models. Okay, now let's move on to tiling.
Tiling, that was like setting up a forward supply depot using that faster shared memory. How does that work with matrix multiplication?
So in matrix multiplication, you can divide the matrices into smaller blocks or tiles and load them into shared memory. So the threads in a block can reuse that data multiple times without going back to global memory.
It's like having those shared tents closer to the front lines so the soldiers can grab what they need quickly.
Perfect analogy. The code for tiling, you have to carefully coordinate how those threads are loading and accessing these tiles, making sure they don't, overwrite each other's data or try to access data that isn't loaded yet. Synchronization is key here.
You mentioned sync threads before in CUDA. That's what we use to synchronize the threads.
That's right. Synchronization is essential for tiling to work correctly. And the performance gains are really impressive. Like, benchmarks have shown that tiling can boost memory throughput to over 400 EB per second, and it can cut the kernel execution time by up to 43%.
Wow. Those are serious numbers. And getting to 6.6 TFL ops is just incredible.
It is, yeah. But even with tiling, there can still be some bottlenecks. Shared memory access is faster than global memory, sure, but it can still cause stalls if too many threads are trying to access it at once.
So even with those forward supply depots, there's still some waiting time.
Yeah, and that's where thread coarsening comes in.
That's when we, merge multiple threads, right? So it's like one soldier carrying multiple supplies instead of many soldiers each carrying one.
Precisely. We reduce the number of shared memory accesses, which minimizes those stalls and improves performance.
Less congestion, things move faster.
Okay, and what about minimizing control divergence?
Right, so control divergence happens when threads within a warp, they take different paths because of branching in the code, like those soldiers getting separated, and then they have to wait for each other, which slows everything down.
So to be really efficient, we want to keep all those threads in sync.
Exactly. That means being smart about how you structure the code to minimize branching, especially within those warp computations.
So we've covered a lot: memory coalescing, tiling, thread coarsening, and minimizing control divergence. It's amazing how much we can optimize these kernels.
And even if you're not writing the kernels yourself, understanding these concepts can give you a much better understanding of how GPUs actually work. It's like a behind-the-scenes look at high-performance computing. Absolutely. This whole deep dive has been incredible. We've learned about GPU architecture, memory hierarchies, kernel optimization, flash attention, and even mixed precision training. It's amazing how much depth there is to this.
It really is. And we hope this deep dive has been useful for you, given you some insights into how GPUs work and how we unlock their true potential.
So to wrap things up, GPUs really thrive on parallelism and efficient memory access. Optimizing those kernels is key to getting the best performance. Techniques like memory coalescing, tiling, and thread coarsening are super important. We also explored flash attention and mixed precision training, which are pushing the boundaries of deep learning. And while the world of GPUs is always changing, these fundamental principles we've talked about, they're going to be essential for anyone who wants to harness the power of these amazing processors.
Yeah, I think that's a great summary. The pursuit of performance is never over. And as new hardware and software come out, the quest to optimize GPUs will just keep driving things forward, in AI, scientific computing, and all sorts of other fields.
Well, thanks for joining us on this deep dive into GPUs. We hope you enjoy it, and we'll see you next time as we explore another exciting area of tech.